let's start in here with moles versus pressure. So let's think about how does the number of gas particles affect the frequency of collisions. If you have more particles of gas, how will that affect the number of times particles of gas collide with the walls of the container? Now this should be pretty straightforward to figure out. If you have a single particle of gas in a container, it's not going to hit the walls of the container very often. There's not going to be very many collisions. If instead you have a mole of gas, so you have 6.02 times 10 to the 23rd gas particles, those are going to be hitting the walls of the container a whole lot more often than just a single atom. So the larger the number of gas particles, so if we increase the number of gas particles, the pressure is going to increase. And this should make logical sense. And the same thing is going to be true if instead of considering moles and pressure, if we consider moles and volume. So if we just cross that out and say volume instead of pressure, so if we're holding the pressure constant and the size of the volume can change instead, it's going to be true for that as well. If you increase the number of moles of gas, then the volume will increase. You can think about it like blowing up a balloon. A balloon has to be at the same pressure as the atmosphere, just by definition, because if it was not, then the atmosphere would either let it expand or let it contract until it was the same pressure. So if you blow into a balloon, what you're doing there is you're putting more gas, more moles of gas into the balloon, and what happens? It doesn't shrink, that's for sure. It gets bigger. And so these two are related to each other. As the number of moles increases, the pressure will increase if everything else is held constant, and if the number of moles is increased, then the volume also increases if everything else is held constant. So the relationship between volume and moles is what we call Avogadro's law. The relationship between moles and pressure, by the way, I believe that is called Gay-Lussac. I forget, Gay-Lussac maybe? I forget the guy's name, but that has its own law as well. But we're going to focus on volume and number of moles here. So again, it's very similar to the last simple gas law that we saw. We're going to use this version of the equation, where the volume divided by the number of moles is equal to the volume at some other state divided by the number of moles at that other state. And so very, very similar to Charles's law. If you go back here to Charles's law, as you increase the temperature, the volume increased. Same thing here with Avogadro's law. If you increase the number of moles, then the volume increases. All right, so very, very similar. Let's go ahead and do a practice problem with this. So like the previous ones, I would encourage you to try to work this out on your own if you can. So you can pause the video now to do that. So we have a 4.8 liter sample of helium gas. So I'm just going to go ahead and say that is V1. And it contains 0.22 moles of helium. How many additional moles of helium should you add to the sample to obtain a volume of 6.4 liters? So if we want a volume of 6.4, how many moles of gas do we need to put in to do that? Okay, so this is what we're looking for here. So the equation for Avogadro's law, V1 over N1 is equal to V2 over N2. We are trying to find N2, so we're going to have to do some more algebra here, kind of similar to what we did last time. So if we multiply both sides by N2, N2, fix that there. So we multiply both sides by n2. That is going to cancel out, leaving us with n2 times v1 over n1 is equal to v2. But we want n2 by itself, so what we're going to do there is we're going to go ahead and multiply both sides by n1 over v1. And so that will cancel those, leaving us with just n2 over there. And so we will have n2 is equal to v2 times n1 over v1. So hopefully you were able to follow that algebra we did there. That's algebra that you should be able to do. It's pretty straightforward. It's just multiplication and division, nothing too crazy. But it is a little bit more than we're used to seeing, just because almost everything in the entire equation moved. But for now, we'll go ahead and plug in what we know. So n2 is going to be equal to v2, which was 6.4 liters, times n1, which is 0.22 moles, over v1, which is 4.8 liters. So our liters here cancel out, leaving us with moles, which is good. And if we do the math, 6.4 times 0.22 divided by 4.8, we get 0.293 moles. Now, if you did this problem on your own and you stopped here, you were mostly correct. You actually have one more step beyond this. This is another situation here where it's important to recognize what you're actually trying to find. So in the question it says, how many additional moles of helium gas should you add to the sample? This number that we found, that's not the number of moles of gas that we added. That's the number of moles of gas at the second state. So when we get to 6.4 liters, we will have 0.293 moles. That doesn't mean that we added 0.293 moles. We started with 0.22 moles to begin with. And so what we're actually looking for here is actually this minus 0.22, which is what we started with. So to get to that second state there, we actually had to add 0.073 moles of gas. So that's actually what we were looking for, was the number of moles that we had to add in to get to that second state. So it's careful. We need to be careful to recognize what we're actually looking for in these problems, because it can be easy to think, okay, I solved an equation, I'm done. But just because you solved an equation does not necessarily mean that what the equation gave you is what you were actually looking for. It could be close, could be very closely related to what you were looking for, but it does not necessarily mean that that is what you were actually looking for, what your final goal was. All right, so let's take those three laws that we just looked at, Charles's law, Boyle's law, and Avogadro's law, and let's combine them to make an even more useful equation. So here we have Captain Ideal Gas law. By your equations combined, we can make a new equation. And if you're interested in how we got this equation from the previous ones, I encourage you to look at the book. I believe they do work through the derivation process of combining those three laws to give us this one. And it truly is a combination of simple gas laws that leads us to this, what we call the ideal gas law. And it's not called the ideal gas law because we're saying this equation is greater than any other equation out there. It is the ideal equation. Now, it's called the ideal gas law because it's describing how an ideal gas will behave. So the gas is the thing that's ideal, not the equation. Not to beat up on the equation. I actually quite like this equation. This is going to sound extraordinarily nerdy, but this is probably in my top 3 favorite equations in existence. And yes, I have thought about favorite equations. Anyway, moving on. So, ideal gas law. PV equals nRT. The pressure times the volume of a gas is equal to the number of moles of that gas times R, which is a constant that we'll talk about in just a second, times the temperature in Kelvin. So pressure times volume is equal to number of moles times a constant times the temperature. Now this R value is something that we have not seen before. It comes up all over the place actually in science. It is not just for gases. It's also very close. Essentially, it's related to the energy of moving particles. Is kind of where it goes back to originally, but it does show up all over the place. Excuse me, this gas constant. But the value for this constant is shown right here. It is 0.0821 liters times atmospheres divided by mole K. And that it's not molk, that is moles times Kelvin. So there really should be kind of a dot there to show that those are multiplied together. So liter atmospheres per mole K. And by the way, when I learned this, I learned it as 0.08206. So if I accidentally go back to doing it that way, it's not really super important that it be one or the other. Either one is fine. But this is an extremely, extremely useful equation. We can kind of make a related equation here. This is what we call the combined gas law. And you can either derive this from the ideal gas law, or you could also derive it from the simple gas laws. Either way, you can get it from either one. You can, I think, more easily see it being derived from the ideal gas law. So just for example here, if we were saying we have a sample of gas, and the only thing that can possibly change are the temperature, pressure, and volume, so the number of moles is held constant. If we divide both sides by T, so that the temperature here goes away, then we would have P times V divided by the temperature is equal to a number of moles times a constant. And so if we are holding the number of moles constant, then all of this is actually just a constant. And so no matter what changes we do to the pressure, volume, and temperature, if the number of moles is the same, then one group of pressure, volume, and temperature is going to be equal to any other setting, so to speak, of the pressure, volume, and temperature. So you can derive it from the ideal gas law in that way, or like I said, you could also get it from the simple gas laws, just depending on which direction you want to go. But both of these are quite useful. Sometimes the ideal gas law is more useful, sometimes the combined gas law here is more useful. It just depends on what you're looking for and what's happening to the gas. If all you're looking for is I have a gas and nothing is changing, I'm just looking for one thing in the gas, one property of the gas, usually the ideal gas law is what you're going to use. If you have a sample that is changing, then it might be better to use the combined gas law. If it's a very simple change, you might go back and use one of the simple gas laws that we've already looked at. But if you have multiple things changing, you're going to be using the combined gas law. So the ideal gas law is used to make calculations of a gas at rest. Like I said, if nothing is changing, we're just interested in finding one of these things, then the ideal gas law is what we're going to be using. The pressure, volume, number of moles, and temperature that we use in the equation must have the same units as R. So the pressure that we use has to be atmospheres, the volume has to be liters, not milliliters. It's a common mistake because we're used to kind of just using one or the other. Most of the time we don't care which one we use. We do care now. Same thing with the temperature down here. Sometimes we used to use degrees C. Not now. We do not use degrees C. We must be in Kelvin. All right. So this is a nice little table here that summarizes the simple gas laws. and how they relate to the ideal gas law. So this is just this entire column here is just taking the ideal gas law and doing algebra to it, so you can see it in different forms. But this is all the same equation, just with things flipped around and not in the same position as they are up here in the original one. And then these are all these simple gas laws and the relationships between everything else. And so only 4 of these simple gas laws have a name. This one actually does not. So actually I misremembered. It wasn't Gay-Lussac that was the pressure and number of moles. That was the pressure and temperature is Gay-Lussac's law. Alright, so this is just kind of a handy thing for you to come back to as you're working through homeworks and things like that. I think I'm going to call it here actually for this video, because if I work through these problems right now, this is going to end up being like a 30-minute long video. So we're going to call it here for this one. We're going to come back in the next video and work through these problems. So I will see you all in the next one.